Hello, my fellow Almontians, and welcome back to another broadcast from the bunker. Today, we're going to go over the River Erosion Lab that you've been working on since yesterday. Graph was a little tricky. I got a lot of questions from you guys about that. I'll make sure I go over that thoroughly. But this lab is all about horizontal sorting and the force of water being able to transport things great distances. And of course, the faster the water goes, the bigger the particles it can transport. And this lab went into different speeds of the river and how it transported different size sediments, etc. All right. So hopefully you read the little funny intro there. All right. The infamous Grand Canyon was carved into the earth by the Colorado River over millions of years ago. So the next time you hop in that lazy river for a swim, be careful. You don't know where you're going to end up. All right, I want to start out with a quick little clip of a whitewater rafting trip. This is the best time to go rafting is in the spring. You get all that melt from the snow, plus springtime brings a lot of rain, right? April showers bring May flowers. So anyway, this is during a springtime rafting trip. Check this out.
Camera guys, take a look over at that nice lady. Yeah. Have a high five up top.
All right, they call that white water for obvious reasons. That water's moving pretty fast, and of course will transport all different size sediments. Very easy to get thrown out of the boat. You notice they're wearing helmets, right, and life jackets. But the more rain you get, the more snow melt you get, the more exciting the trip is. All right, pretty cool stuff. All right, so let's get rolling into it. Hopefully you define your vocabulary. Make sure, the lab is 100% complete before you submit, of course. The procedure was here. The setup in school we did would have been way bigger than that. We actually set up a channel about 8 feet long. It extends across the front of the room. We were going to drop different size sediments in there to represent, of course, different particles. We were going to change the amount of flow. And that, of course, would affect the amount of water in the river. That's called discharge, right? The amount of water in the river. And the more water in the river, the faster it goes. We were also going to change the slope of the tube. And that, of course, would change not only the speed of the river, but, of course, the age. Because if you remember, younger rivers are steeper. And as rivers get older, they become less steep and they slow down. So all of those variables we were going to try to take into account using a similar model as in that picture. All right, this was the data chart that I forwarded to you guys in the GC. The distance of the river in this chart, we put down 200 centimeters. And this was ideal data, right? In the class, obviously, things changed. We would have gotten some other numbers. But this is ideal data to help you understand how the reference table chart would work with particle size and erosion. Okay? We'll start out over here. I left question marks here. You were supposed to figure out what goes in there. What age would that river be? Well, if it's only a 5-degree slope, right, that's very low, so you'd have to infer, that must be an older river. So yes, hopefully you put in there old. And as we go down the chart, you'll notice 5 went to 10, 10 went to 15, and that means the river is getting, of course, much, much steeper, indicating a younger river. So in this sense, as you go down the chart, you're kind of going back in time, right? The river would be getting younger as you go down the chart. So we'll fix that up real quick here. I'll erase my question marks. The 5-degree slope we're going to call the old river, right? Old Man River. 10, not as old, we'll call that mature. And the 15 is a youthful stream, right? A very young river, it's still steep. It hasn't cut down as deeply because it's still young, but someday it will cut much down. And the goal, right, a funny way of looking at it, the goal of rivers is to cut down to sea level. Once they do, their flow will slow down greatly because sea level is generally your lowest point. And if you're already at sea level, then you don't have much of a slope, and the river goes even slower. So that's what's going on there, old, mature, and young. Now, you'll notice the faucet settings, low, high, low, high, low, high. And in the classroom, we would have changed that. But Mother Nature does it differently, right? If it's a low flow, that means there hasn't been much rain. It's probably pretty hot, so a lot of the river water evaporates. You're probably in like late summer. Lots of areas will start to go into drought, a deficit of water. So you'll have a low flow in the rivers, and some might even stop flowing altogether. Okay? As far as the high flow, well, that's when Mother Nature really turns the faucet on, right? You get crazy April showers. You're getting your snow melt from the previous winter, and all that water goes downhill by the pull of gravity and ends up in the rivers. So when you see this high flow, you're thinking springtime, and that's why I labeled the seasons for you here. Low is going to be your summer. If you're going to go rafting in the summer, it's going to be kind of a boring trip, right? The river's going slow. But springtime, boy, oh boy, is that the time to go. Now, it'll be a little chilly, and that water is going to be chilly as well, right, from the snow melt, but that'll be the rush of your life. So that's what the seasons were all about. And the travel times, in the classroom, we would have had a timer. And the second the sediment was deposited, the clock starts, and then when it falls over the waterfall at the end, right at the end of that tube, right into the bucket here, that's when you would stop the clock. So the travel time was literally from here to here. All right? Those times there, again, they're ideal times to work with the chart, and you'll see what I mean. So some of you, I think, are a little, scared by the numbers, but it's a rate formula, distance divided by time. So you simply did 200 divided by 600 for your first one there. 200 divided by 600. And you got a number, a monster number 0.3 repeating. Well, don't be afraid of that. You just write in, right? That's about 0.3. Okay, do a couple more, but I think you'll get the gist here. The next one there, distance over time. Well, 200 divided by 200, you don't even need a calculator for that. Right, that's simply 1.0. Jumping down, I'm going to skip around, and I'm not going to do the whole thing here, but let's say this one here, right? 200 divided by 50. So you could plug that in if you like. 200 is your distance, divided by 50 was your time, and you got a whopping 4, and that's centimeters per second. Right, the units are up there for you. And the last one, of course, here, 200 centimeters. It did it in 1 second. That's extremely fast. 200 divided by 1, of course, is simply 200. All right. You know what? I'll plug the rest of them in as well, just so that the chart makes sense to you. So the third one there was 0.67. And the other one missing there was 13.3. So I know some of those numbers seem strange, but yes, those are the correct numbers. Now, how do you fill in this next part? Well, you got to use the reference tables. Again, you got to take your velocity, go to the reference table chart, and figure out what size sediment would be eroded. So let's jump to that chart right here. The first velocity we calculated was 0.3 centimeters a second. Now, that sounds slow to you. You're not crazy. That is extremely slow. 0.3 is somewhere on the bottom here, right? That's 0.1. That's 0.5. So 0.3 is right around there. And you would go up to the black line. And anything below this curvy black line will be eroded. Okay? The water's going fast enough to erode it. So 0.3 we said was about there. I'm going to go up to that black line. Right there. And now if you go over, there's already a dashed line there, but if you go over, you end up right about here. Now what's below that black line? Silt and clay, and those two particles would be eroded if the river was going 0.3 centimeters a second. So you go back to your lab, and you say, all right, 0.3 centimeters a second. What do we say was going to be eroded? Well, we said silt and clay. So you give check marks to silt and clay. All right, jump down to the next one here. Let's go to 4, for example. 4 centimeters a second. Well, what size particles would that erode? Go back to your chart. 4 centimeters a second. Well, that's right around there this time. I'm going to go up from 4. Obviously, my line is a little crooked. I go over, and son of a gun, now we can erode bigger things because the water's going faster, and that means it'll erode bigger things. So this time you're going to check off sand. Now, this is all of sand. It's got a big range, 0.2 to 0.006. That's a big range. If you remember in the sedimentary lab, I asked you to feel the rocks with your thumb in particular to feel the different size grains. Well, fine sand is closer to 0.006. That's very smooth. We said if you're doing woodwork, right, that would be for more of a fine finish sanding. Versus a 0.2, well, if you're doing sanding with a 0.2, that's not going to be a finished smooth product. That's still going to be pretty rough. But anyways, so that would be coarse sand up top, medium sand, and down toward the bottom is fine sand. And that's why the chart is broken into those 3 parts. So here I can erode the finer, the medium, and just some of the coarse, but you would definitely check off a medium, fine, silt, and clay. So go back to your chart, and that was for a 4. So we would check off the clay, the silt, the fine sand, and maybe a little baby check there for the coarse sand. All right? It didn't get all of the coarse sand, but it got some, so we'll put a little baby check. All right, I'll skip down to the last one here. 200 centimeters a second, folks. That is insanely fast for a river. And because of that, it was certainly happening in the spring, and you're going to push lots of big things. Okay? 200 centimeters a second, you would go to the chart, would be right about here. Go up, and what are you eroding? Just about to there, right? Just about to there. So you would do everything under that line would get eroded. So now it would be clay, silt, sand, all the pebbles, and just start to move some cobbles. Now you wouldn't move the big ones, and you certainly wouldn't push a boulder yet. But that would be some serious erosion. And if your house was near a river flowing 200 centimeters a second, you better put a life jacket on because you're going for a swim. So check off the appropriate sediments that would be eroded. So we'll start from the small. Definitely clay, the silt, all the sand, all the pebbles, right? The small, medium, and large pebbles. And just a little baby check on the bottom because it would also start to move some cobbles. And that's what was going on that chart. You had to check off the appropriate particles that would get eroded based on the velocity you calculated. Okay, slide on down to the graph here, and you had to plot that data. Now the data we're plotting, if you take a look on the y-axis, that's velocity, right? Down below is slope, how steep the river is. But there's going to be 2 lines because remember, we had data from summer and data from spring. So it's again 2 lines on a graph, but not like last time. There's no y2 axis this time. You're going to just plot the same 2 lines using the x and the y. So, for your first set of data, what I recommend doing, we'll start with, say, the summer line. So I need to do a 5 from summer, a 10 from summer, and a 15 from summer. So I'm going to circle those, and maybe we'll change colors here. Do it in a little green. So let's say we're going to plot this guy, and this guy, which is going to be this guy, and that guy, right? So those are the different slopes and those are the velocities you calculated. Now it's a little crazy because the range of data goes from 0.3 to 200, 0 to 200 for all intents and purposes. So when you set up the y-axis, going to be a little tough to see the graph because, you know, the data is kind of all scrunched together. But if you count the number of boxes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You got about 15 boxes. So you would take 200 and divide by 15, right? So you got your calculator handy. So we have 200 is our range of data. Dividing by those 15 boxes, and you're getting about 13.3. Now, what kind of interval is that? Nobody does that. But we're going to round that to a 15. And you guys are really, really good at skipping by 15s because that's the magic number of the Earth's... Anybody? The Earth's rotation. Remember that? 15 degrees per hour. So you should be able to knock off 15 degrees per hour pretty fast. It's also the number of degrees time zone skips by, right? So that should be pretty easy for you to skip by on that y-axis because it's a pretty common number in earth science. So 15, 30, 45, 60, etc. And that's what you should put on your y-axis. Now, I'm not going to be able to squeeze them all on with my fat pen here, but so 15, 30, 45, 60, 75, 90, 105, right, I would get up to, in the end, 200 something. 210 would be my last point. So squeeze in there as neatly as you can. My marker is going to start bleeding together, but you should do it as neatly as possible. Every box is worth 15. All right? So let's get a hold of some data here. We have a 5-degree slope at a 0.3. 5-degree slope at 0.3, well, that would be very close to the 0, something like that. Your second point, of course, 10-degree slope at a 0.67. Well, that's not much higher. And the last one there, 15 at 13.3, just barely makes it to the top of the first box there. So this line is a very gentle slope. Connect your line and circle your points. That's a terrible line. Let me fix that one. And not too much better. All right. Now that is, if you remember, that's your summer data. So you're going to label that summer. I'm going to change colors on mine, but then we're going to do spring. Okay? So I'll just put summer next to that here. And in the summer, the rivers go much slower. All right, now I'm going to switch colors. Maybe a red this time. And now we're going to plot spring, which of course is going to be this one, and that one. And for velocity, it's this guy, and this guy. All right, so get it on there. 5 degree was a 1.0. 5 degree, very close to that first green point. The 10 degree, the mature river, was a 4. And again, not too much higher than that second point as well. But that last point, 15 degrees, 200, that almost goes off the charts, folks. 15 degrees, 200, you are somewhere up here-ish. And now when I connect those, boom. Look at that different rate of flow, right? The more water you have, the more discharge, the steeper it is. That springtime flow is almost off the charts. So we'll label that one spring. So a strange graph, but with the data set we had, that's the best we can do for now. Unless you're going to start putting breaks in there, right? The little squiggly lightning bolt. But this is a consistent interval, and that's what your graph should look like. As far as your questions in the end there, I'll go through a few of these here. What causes the discharge to vary? Well, discharge, remember, is the amount of water in a river. So if there's more rain, if there's snow melt, all of that will certainly change the amount of water in the river. If it's a very, very hot summer, right, the water will go down. The water table gets lower and the rivers will have less water in them. If the slope remained constant, what would happen to velocity if your discharge increased? Well, again, that word discharge means the amount... The amount of, what did I do there? Yeah, we'll just keep that up there. But anyway, Where were we? Number 3, if the discharge remained constant. Now it's if the water remains constant, what will happen to velocity if the slope increases? Well, you've been on a steep slide at Splish Splash or anywhere in a park. The steeper the slide, the faster it's going to go. For number 4, at any given velocity, what takes longer to transport, silt or sand? Well, the heavier thing will always take longer to transport, the bigger, heavier thing. So sand, because it's bigger, heavier, requires more energy, right? The faster water to go. This one, 5, as slope increases, what happens to the rate of erosion? Well, again, steeper slope means gravity is going to pull things down faster. You're going to get more erosion. Okay. The 6th one, again, now we're adding more water again. What would happen to erosion? Well, more flowing water means more erosion there. Is there a relationship between volume and slope and the size of the sediments? Well, I think at this point you got it, right? The steeper the slope, the more water there is, the more erosion you're going to get. So put that together in like an as relationship statement. Number 8, why does velocity change from season to season? There you want to make reference to melting snow or spring rains, hot summer temperatures, things like that. And for the summary, probably the most important question on the lab, if you were thinking of buying a home near a river, now they are beautiful settings, very serene, of course, but you better consider certain factors, as far as erosion throughout the year. Remember with streams, right, what side of the curve is important. Don't forget that, those meanders. So that's a biggie, of course, how close to the river you are, what is the age of that river. You better consider all those things before you make the biggest investment of your life, which is usually somebody's home. All right. Hope that cleared it up for you. The lab should have been handed in at this point. If not, you will, of course, lose some credit for being late on that. Don't forget, if you do have additional questions, simply type them into the YouTube section below, or there's the remind code once again. All right? All right, folks, get outside and enjoy some sun, and I'll see you tomorrow.